So we've seen the first isomorphism theorem for groups. Here's the same statement, but for rings. If I have an onto ring homomorphism from a ring R to a ring S, then the factor ring R mod the kernel is isomorphic to S. So here's the proof. If you want to show two rings are isomorphic, you need a bijection from the first ring to the other that's also a homomorphism. So I'll do that. I'll define a function f from R mod the kernel to S, and I'm going to define it by sending an element in this factor ring. Elements in this factor ring look like R plus the kernel. The kernel isn't ideal, so this factor ring actually makes sense. I'm going to send this to an element in S by sending this term to phi of R, which lands me in S. So this is actually the same function that we use to prove that the first isomorphism theorem for groups holds. So we've already done a lot of the work in checking that this has the desired properties. By the first isomorphism theorem for groups, this function f we already know is well defined. We know it is 1-to-1. We know it's onto because that's stated in the statement of the theorem. So it's a bijection. And we know that f splits over addition. So the only thing that's new here for rings is the multiplication. So that's the only thing I have to check that f works well with. So we only need to check that f splits over multiplication. So let's check that. If I take two terms in the factor group and multiply them, so R1 plus the kernel times R2 plus the kernel, and I multiply them, definition of multiplication in the factor ring is f of R1, R2 plus the kernel. The definition of this function sends this term to phi of R1, R2. Now, phi is a ring homomorphism. It splits over addition and sums. So this is phi of R1 times phi of R2, which of course is f of R1 plus the kernel times f of R2 plus the kernel. That shows the desired property. Everything else follows from the theorem that we proved last quarter about groups. So that's the end of the theorem. Let's do a couple of examples. So examples. So let's let phi go from z to zn be defined by sending an element a in z, an integer, to a mod n. What does the first isomorphism theorem say? This is definitely an onto homomorphism. I can get every possible remainder I'd like. So the statement of the theorem is satisfied. So this says z mod the kernel is every multiple of n, so nz, should be isomorphic as a ring to zn. Another example. How about we let phi be the evaluation homomorphism? So I could take any polynomial with real coefficients, and I could send it to a real number, and I could define it by telling you that a polynomial should be evaluated at 9. So I'm going to plug in 9 for x, turn my polynomial into a real number. Well, then the kernel, I think we've seen in a previous video, the kernel is polynomials of the form x minus 9 times q of x, where q of x is a polynomial. The first isomorphism theorem for rings says that my ring of polynomials mod this kernel should be isomorphic to R. In this case, it is true that I have an onto ring homomorphism. So if you'd like to graphically depict the first isomorphism theorem with a diagram, we could do so. We have a ring R, and R is sent to another ring S by phi, and that's got to be an onto. You could take elements in the ring R and send them to the factor group R mod the kernel. The function that does that is the natural ring homomorphism. Let's call it eta. And here what I'm saying is eta sends an element in R, the ring, and gives you an element in the factor ring, R plus the kernel. The natural thing to do, the natural homomorphism. And then in the proof of this theorem, we took elements in the factor group and turned them back into elements in S. That was our function f. So there's a diagram that depicts what's going on in the first isomorphism theorem for rings.